My name is Novozhilov, and I'm a head of HPC and Highly Nonlinear Simulation Department at CADFEM CIS. And today I want to tell you about aircraft NPP impact simulation methodology. First of all, let me quickly introduce myself. I'm a Master of Science at Saint-Petersburg State Polytechnic University, and I'm with ANSYS, LS-DYNA, and finite element simulation since 2K6. So the engineering is one of my biggest passion. On the slide you can see quick agenda for today. I will talk about problem introduction, reinforced concrete modeling, test cases, load condition and aircraft simulation, full-scale simulation, and then we will talk about conclusions. Problem introduction. So, nuclear power plant, or NPP, is a huge complex of buildings and constructions. The most important part of NPP is containment. This is a building where the reactor is placed. So this building should be protected from many load types. When you are planning to design NPP, you should take into account many natural catastrophes and extremal conditions depending on the place where the NPP will be constructed. That could be earthquakes, tsunami waves, tornado, snowstorm, and then even mud flow. When you are planning to develop NPP, some of these conditions, or maybe mixture of these conditions acting simultaneously, should be taken into account. But nowadays, we can find the new type of technogenic man-made catastrophe, the impact of large commercial aircraft into the building. On the slide you can see that modern large commercial aircraft is big enough, even with comparison to NPP containment. When you start this size of project with buildings and aircrafts and nuclear power plant, you may have a lot of questions. Some of these questions is already answered in the books and reports. For example, very good handbook for me is SRS 87 from International Atomic Agency. In this book you can find basic guideline how to start this type of simulation. But even if you see the answer in this book, this answer should be checked twice, because we are talking about NPP. Let's look at our assumption of reinforced concrete modeling. So, reinforced concrete civil structures made of steel and concrete. And when we're talking about NPP, you can see a lot of steel and concrete. So, we need to simulate steel, we need to simulate concrete, and we need to be able to couple steel and concrete together. If we are talking about steel and reinforcement, we can see that many reinforcement rods immersed inside concrete form some kind of rebar cage. And this cage allows maintain construction structural integrity even after concrete fragmentation. International Atomic Agency declared to use Cowper-Simon strain rate model for this type of simulation, for simulation of reinforcement inside concrete. We can easily implement this kind of model inside LS-DYNA. And now we can go to the concrete. LS-DYNA has more than 10 special concrete models to simulate concrete behavior. And we choose CSCM concrete model because this model has many advantages, such as, for example, 3 invariant yield surface, damage-based softening with erosion, strain rates effects. And one of the most important features of this model for us is the ability to generate input based on 3 value, density, concrete strength, and aggregate size. At the design stage of NPP, you have not many experimental data about concrete. You can only know for sure the concrete strength. This is our input and that what CSCM model demand to start simulation. So with this model, we done some tests and we get some interesting results. For example, with single element tension and compression, this model shows significant error in extreme concrete strength prediction. You can see on the slide curves at the right side. Blue curve, it's built-in calibration procedure result. So we can see that error can be up to 50%. This is unacceptable. So we create our new external input initialization procedure in form of Python script. That procedure allows us to significantly reduce error estimation. For example, for concrete with strength 50 megapascal, we can reduce strength estimation prediction for single element from 30% to 5%. This is very huge improvement in model work. With this model input, we developed set of tests to validate and verify model work. I can show you two main tests in our set. Other test description you can find in the paper for this research. Our first test is low impact to the reinforced concrete beam. In original paper you can find 16 experiments. We take 4 from this list with maximal deflection and maximal damage. And with these 4 tests we study such feature as the mesh influence, work of constrained beam in solid card, ability to correctly describe beam deflection and contact force. And we also study what is the difference between crack pattern in real experiment and damage pattern in simulation. Our one of the main result is that the constrained beam in solid could work correctly and give the same result as a merge node approach. So we can use this type of reinforcing coupling. And also we can show you that we can correctly describe force reaction and beam deflection. Our second test is the mapping slab test. This is very famous test with reinforced concrete under high-speed deformable projectile impact. The main feature of this experiment is that the cross-section size of the projectile, the diameter, is bigger than the rebar spacing. So when the projectile interacts with wall, it interacts not only with concrete but with full rebar cage. And this is very interesting that we should simulate. So results showed for 3 type of mesh, 3 size of mesh, and you can find the legend at the bottom of the slide. Our first set of results from this experiment shows that we can correctly describe the force history, and also we can correctly describe displacement history. The only possible result that could be improved is the peak displacement in the area near the impact zone, but that could be improved with a new type of mesh and with material erosion. Currently in our model we do not use material erosion and element death. The second part of result study is mesh sensitivity and stability in terms of damage. You can see the damage results for 3 different mesh sizes. And with these mesh sizes you can see that if we use finer mesh we get better results. And for 50 millimeters, for example, you can see correlation between real crack pattern from experiments and results from simulation. So unfortunately, if you keep decrease element size, that will not give you better result. Our research with mesh 30 millimeters shows these effects. While construction is out under the loading, the result is good and the correct pattern is absolutely clear seen. But after the loading is finished and when the construction starts oscillate near new position of equilibrium, you can see unphysical damage accumulation in the concrete. We linked this effect to forming entire and completely unreinforced layer of concrete outside the rebar cage with this element size. And this layer of element accumulate damage, so you can see the strain softening but no mass reduction. And this fact leads to material lose stability. If you do not use element erosion, you should keep in mind that the concrete cover thickness is the bottom element size limit. So let's talk now about aircraft simulation and loading applications. RIERA methodology widely used for simulate this type of loading. So RIERA assumed that aircraft could be simulated as a plastic rod which impacts rigid, fixed, flat target that cannot move, and the impact is normal impact. Then the reaction force from impact will be assumed as a sum of aircraft strength and aircraft impulse. When you are talking about NPP is not a rigid construction, it's flexible. And also this construction not flat. This construction can have complex shape and the impact could be not normal, could be with some angle. Direct aircraft simulation should be used to simulate aircraft impact loading. On this slide you can see the video from the only public available experiment with a Phantom F4 impacting reinforced concrete wall. You can see that these aircraft basically do not decelerate during impact, and also that the aircraft after the impact transfers from a solid state to dust. With this impact we developed our own procedure to generate and calibrate material model and aircraft model to applying the load. So our main ideas of model development. We need to deliver load. Do not think about aircraft. So we decide to transfer maximum load through impulse. We use mud honeycomb to simulate aircraft as ideally plastic compressible rod. To describe this type of deformation, we assume to simulate aircraft as ALE body, and then this body will transfer the impact load through FSI. So the results of our work. For example, you can see the model calibrated to represent Boeing jumbo jet impact. So the curve blue color is a curve from RIERA input, and the red curve is a result of fluid structure interaction reaction from our ALE model. You can see that our curve is pretty the same that the input curve, and also our curve is noiseless. This is a natural feature of FSI interface. You will not see noise and the reaction will be smooth. This will allow us precisely transfer aircraft load to any structure. Now we can talk about full-scale simulation, since we can simulate concrete and aircraft. As I said at the first slide of my presentation, nuclear power plant is very huge and complex construction, and we will talk about containment, the most important part of this building. You can see the cross-section sketch of NPP containment, and this NPP could be divided to separate outer containment and inner containment part, which connected together through basement slab. Now we can simulate only outer containment, because this part of the containment will take all the load. And we could also check if the outer containment will not touch inner containment, because inner containment contains many very important equipment. We should check that outer containment will keep the integrity and will not touch inner containment. And with this task, we also have the problem how to find the correct element size for this type of simulation. So to define the correct element size, we create a numerical model of two different reinforced concrete walls with 4 different thicknesses. And we start to measure maximum wall deflection under Boeing impact load to define the good mesh. This is one set of the results from our simulation. You can see that for this type of reinforced concrete wall, the 300 millimeters mesh is enough to precisely describe wall deflection. With decreasing element size for mesh, you could better describe the crack pattern, but this is not the main aim of our study. We analyze complete set of data, and we decide to use the element size 200 millimeters, which enough for any kind of walls from our set. With all this knowledge, we now can create precise outer containment model that will carefully represents all physics and geometrical properties of our building. Our model contains all bending and shear rebars explicitly. So this is possible to develop this size of model with ANSYS meshing and usage of LSTC LS prepost. As you can see, the size of elements in solid is about 200 millimeters, and we use all hex mesh. This is high quality mesh with element quality about 1. This allows us to run this simulation very fast. For one simulation, 1 second of experimental time, you can spend only 100 hours of 64 HPC cores, and this for the model with about 66 million degrees of freedom. I also want to mention help of Mr. Hao Chen, which helps us to debug and to find the issue with memory allocation for constrained beam and solid algorithm with this size of models. Why we can use such a big model? This model is easy to use in different loading scenarios. For example, you do not need to spend additional time for model development if you decide to simulate another impact scenario, for example, into the roof or near the fuel gate. Also, this model will not provide unnecessity to guess where to simplify or not to simplify the model. We simulate building as it is, and this level of precision, this level of detail we can implement for any building of nuclear power plant. We do not include structural ALE elements in the scope of number of degrees of freedom. And to simplify simulation in these terms, we use mobile SLE domain for our body. So the domain moves with the center of gravity of our aircraft, and this is easy to implement and to simulate. Let's look at the results of this size model. As I said before, concrete is very complex composite-like material made of non-linear steel and non-linear concrete and coupled together in this size building. It's possibly not so easy to understand the results, but we can try to explain how we analyze the results. First of all, we do not use the single criteria for results analysis. The main three criteria for results analysis shown on this slide. We need concrete damage, concrete displacement, and plastic rebar strain. First of all, concrete damage. This is a field of concrete strain softening after extreme loading. So if you see red concrete, this is the concrete for which the maximum, the peak capacity of the strength is reached. And this concrete could have some cracks. But it's not necessarily bad idea to have a crack inside concrete, because we still have huge cage of reinforcing rods. To understand is it bad or is it not to see a red zone of concrete damage in our building, we should take into account concrete displacement and rebar plastic strain. You already see on the slide that the rebar plastic strain is not very big. It's generally about 1 or 2% near the impact zone. And the red 5% plastic strain is only in the shear rebar. Unfortunately, I cannot show you this on the slide, but our result analysis for this experimental case shows that generally plastic strain accumulates inside shear rebars, and the bending rebars is okay. And the last but not least result in our results analysis is the concrete displacement. For simplicity of this presentation, I show you only the sum of all displacements component, but of course it's better to analyze them separately. You can see that our construction oscillate near new position of equilibrium, and the maximum deflection is under the fuselage impact zone. But after the end of the simulation, the general construction displacement is about 4 centimeters only. So we can told that outer containment do not touch inner containment, and this is very good for our approach of separate containment shell simulation. Also, you can see that the maximum deflection is near the aircraft fuselage impact, and this deflection is about 200 millimeters, which also is not a very big value. So for this experimental load and this test containment, we can see that this type of impact is not very critical, and this construction can keep standing. Let's see the conclusion of our simulation methodology. I want to mention that we developed new initialization procedure for CSCM concrete model, and this procedure allows us to significantly, sometimes from 30 to 5%, reduce error in strength estimation. We validate and verify this procedure and all other aspects of reinforced concrete simulations. We developed our own procedure of aircraft model generation, and now we can quickly generate precise model of any type of aircraft by given Rierach curve. We also now able to precisely simulate full-scale building models like NPP or any other building of NPP set. We have great experience with this type of simulation. And to prove our experience, I want to mention that this methodology has been applied since 2016 for NPP development in Finland, China, Hungary, and Russia. Thank you for your attention. My name is Yuri Novozhilov, and you can feel free to contact me and discuss possibility of reinforced concrete simulation. Thank you once more, and bye.